Hello my dear students, welcome to my YouTube channel that's Concepts of Chemistry. Before starting today's lecture, please do subscribe my channel. My dear students, today I'm going to solve some numericals on the Rydberg equation, and before starting the numericals, let me write down the formula for you which I'm going to use for solving this numerical. And the formula is that 1 by lambda is equal to the 109,677 into z square into 1 upon n final square minus 1 upon n initial square. So this is my formula, in which first of all, what is the lambda? This is the wavelength of photon emitted per electronic transition. Per electronic transition. What is Z over here? The Z is atomic number. What is NF? NF is the orbit number. The orbit number in which electron is finally entering. What is Ni? It is the orbit number in which electron was initially present. So this is the formula which I'm going to use for solving the numericals. So let us come to the first numerical. The first numerical is asking, calculate the frequency and the wavelength of a photon emitted when electron makes a transition from fifth orbit to second orbit. Here the orbit is initially present in the fifth orbit, so my Ni comes out to be 5, and the electron is finally entering in the second orbit, so Nf comes out to be 2. What I have to calculate over here? We have to calculate the frequency of the photon emitted and the wavelength of the photon emitted. So let me write down the formula. It's 1 by lambda is equal to the 109,677 into z square into 1 upon n final square minus 1 upon n initial square. So 1 by lambda, it comes out to be 109,677. We are calculating this for the hydrogen atom. For hydrogen, my Z is equal to the 1. So it comes out to be 1 square into 1 upon NF. The final orbit is 2. So it's 2 square minus 1 upon Ni. The orbit in which the electron was initially present, it was the 5, so it comes out to be 5 square. So 1 by lambda comes out to be 109,677 into 1 upon 4 minus 1 upon 5 square is 25, so 1 by 25. So 1 by lambda, it comes out to be 109,677 into 25 minus 4 divided by 25 into 4. I have taken the LCM, and this thing comes out to be 109,677 into 21 divided by 100. So wavelength, I am reciprocating it, the 1 by lambda to lambda. it comes out to be 100 divided by 109677 into 21, and this value comes out to be 4342 angstroms. So the wavelength of the photon emitted during a transition from fifth orbit to second orbit comes out to be 4342 in angstrom units. Now we have to evaluate the frequency. The wavelength, we have got the wavelength, now it's term for the frequency. We know that the formula of frequency in the nu is equal to c upon lambda. Here c is 3 into 10 to the power 8 meters per second. So that means we have to substitute the value of wavelength in the units of meters. So 4342 is angstroms into 10 to the power minus 10. It is converted to meters. So the frequency of the photon emitted comes out to be 6.9 into 10 to the power 14 per second. So this is the frequency of the photon emitted. So we have calculated the wavelength and also the frequency. So this was the first numerical. I hope you understood it. So now let's move to the second numerical. Now the second numerical, it's saying that calculate the wavelength of photon emitted forming the first line and the limiting line of the Balmer series. Now first of all, Balmer series. I'm writing Balmer series. In case of Balmer series, the final orbit number is fixed, that is 2. So the first line will be of electronic transition from the orbit number 3 to 2, and the limiting line will be for the electronic transition from the orbit infinity to the 2. So we have to evaluate the wavelength for the first line and limiting line. So we have got their orbit numbers, the initial and the end final. So let's calculate the wavelength for the first line first. So first of all, we are evaluating for the first line of Balmer series. For the first line of Balmer series, the n initial is 3 and the n final is 2. So now I'm putting the formula. The formula is 1 by lambda is equal to 109677 into 1 upon n final square minus 1 upon n initial square. So 1 by lambda, it comes out to be 109677 into 1 upon n final, the final is 2, is 2 square, minus 1 upon n initial, the n initial is 3, is 3 square. It comes out to be 109677 into 1 by 4 minus 1 by 9. So my 1 by lambda, it comes out to be 109677 into 9 minus 4 divided by 9 into 4. I have taken the LCM, and this thing comes out to be 109677 into 9 minus 4 is 5, and 9 into 4 is 36. So I'm reciprocating the wavelength now. It comes out to be lambda, it comes out to be 36 divided by 109677 into 5. So the wavelength for the first line of Balmer series comes out to be 6565 angstroms. So that's for the first line. So now let's evaluate for the limiting line now. I'm taking the second part of the question. I'm evaluating the wavelength for the limiting line of Balmer series. Limiting line of Balmer series. The limiting line of Balmer series, the n initial comes out to be the infinity and the n final comes out to be the 2. So I'm again putting the formula. Says 1 by lambda is equal to 109677 into 1 upon n final square minus 1 upon n initial square and the bracket closed. So this thing comes out to be 109677 into 1 upon then final is 2 square minus 1 upon n initial is infinity square. So it comes out to be 1 by lambda. So 1 by lambda, it comes out to be 109677 into 1 upon 4 minus 0. So my wavelength comes out to be 4 divided by 109677. My dear students, I will get the wavelength in centimeters over here. I get the wavelength in the centimeters, and at the last I'm converting my centimeters to the angstrom. In the previous questions I have also converted that centimeters to angstrom. Let me come back to the previous question. Here my answer was in centimeter and I have converted that thing in the angstroms in the final answer. So here the final answer of the wavelength, it comes out to be 3647 angstroms. Is 3647 angstroms. So that was my second numerical. I hope you got this thing also. And here also, my dear students, my firstly answer was in centimeter. In the final answer I have converted that unit to angstroms and it was 4342 finally in angstroms. So let's come back to the third numerical. Now what's the third numerical is asking? The third numerical is saying calculate the wavelength of the spectral line obtained in the spectrum of Li2 positive ion. First of all, the Li2 positive ion, my Z comes out to be 3. When the transition takes place between the two orbit number whose sum is the 4 and the difference is 2. So I am writing my orbit number n initial plus the orbit number n final and their sum is 4. Now the n initial minus the n final, their difference is 2. So this thing comes out to be minus plus minus. So it comes out to be 2 and final comes out to be 2. So the n final comes out to be 1. And now the n initial comes out to be 3. So I got the n initial and the n final. Now I'm putting the formula. In the formula I'm saying is 1 by lambda is 109677 into z square into 1 upon n final square minus 1 upon n initial square. In the previous questions the element was hydrogen, said there is z was 1 in the previous question, so I have not taken that z in the main formula, but in this question the atomic number is 3, that's why I have written z in the formula. So now it comes out to be 1 by lambda, it comes out to be 109677 into the atomic number is 3 as 3 square. In the previous question the elements were hydrogen, the z comes out to be 1, so I have not taken the value of z in the main formula. Please don't get confused. The main formula is 109677 into z square, where the z is 3, so I have taken the z to be 3 over here, minus 1 upon n final. Then final is over the 1 over here is 1 square minus 1 upon n initial. The initial n is 3 over here, 3 square, bracket closed. So it comes out to be 1 by lambda, comes out to be 109677 into 3 3 is 9 minus 1 by 1 minus 1 by 9 and the bracket closed, and this thing comes out to be 109677 into 9 into it's 8 upon 9. So that's my lambda. Now my finally wavelength comes out to be 1 divided by 109677 into 8, and this unit is in centimeters. And my final wavelength comes out to be 114 in the units of angstroms. In the final calculations, I'm converting the unit of centimeter to the unit of angstroms, so please don't confused, please don't get confused, sorry. Please don't get confused. So I hope you got this thing. So now let's move to the question number 4. Now I'm talking about the question number 4. The wavelength of certain line in Balmer series observed to be 4341 angstroms. Here the wavelength is given. The wavelength is given to be 4341 angstroms. In the formula we always get the answers in centimeters, so first of all we have to convert this wavelength to centimeters, and it comes out to be 4341 into 10 to the power minus 8 centimeters. Now to what value of Ni does the electron belong? So first of all, it's in Balmer series. For Balmer series, my final orbit number is always equal to 2. Now I have to evaluate the initial orbit number. For Balmer series, the final orbit number is always 2, and here we have to evaluate the initial orbit number. So let's again put the formula. I'm taking 1 by wavelength is equal to the 109677. Again, I'm assuming this element to be hydrogen, so I'm not taking Z over here. So it's 109677 divided by n final square minus 1 upon n initial square and the bracket closed. So this thing comes out to be 109677 into 1 upon n final. N final is 2. It's 2 square minus 1 upon n I square I have to evaluate. And the wavelength is 4341 into 10 to the power minus 8. So in the next step, it comes out to be 1 upon 4341 into 10 to the power minus 8 into 109677. It is equal to the 1 upon 4 minus 1 upon n initial square. So it comes out to be 1 upon 4.7. After whole calculation, it comes out to be 1 by 4.7. It is equal to the 1 upon 4 minus 1 upon n initial square. It comes out to be 1 upon 4.7 minus 1 upon 4. It comes out to be 1 upon n initial square, and this value comes out to be 0.04 equal to the 1 upon n initial square. On reciprocating the both sides, the n initial square comes out to be 25. So my initial orbit number comes out to be 5. So this is the electronic transition from 5th orbit to 2nd orbit. So this is electronic transition. This is electronic transition from 5th orbit to 2nd orbit. So that were the numericals for today, and I think it was the easy one. So I hope you all understood today's numericals. So if any student has some doubts, then he or she can book a paid online class to clear their doubts. My phone number is mentioned on thumbnail of this lecture. Please like, subscribe and share my channel to maximum number of students. Don't forget to press the subscribe button. Stay blessed.